In 1996, a computer program beat a world chess champion. In 2023, artificial intelligence promised to organize all human knowledge. But by 2026, engineers realized a disturbing truth. The world's most advanced language models are fundamentally incapable of knowing what is real. They do not think, they do not remember, and they do not search. They merely guess the next word. And when they guess wrong, the consequences are catastrophic. To understand why AI makes things up, we have to look at how it was born. A large language model does not contain a database of facts. It is not an encyclopedia. Instead, it is a mathematical map of language, constructed by reading billions of web pages. When you ask a model a question, it does not look up the answer. It calculates which word is statistically most likely to follow your prompt. Think of it as a highly sophisticated lossy compression algorithm, like a low-resolution image file. When you zoom in on a compressed image, the pixels look blurry, so your brain fills in the gaps. When a language model hits a gap in its training data, it fills it with plausible-sounding nonsense. In the research literature, this is called factual inconsistency. In the real world, it is a hallucination. And for enterprises relying on these systems for medicine, law, or aviation, a plausible lie is far more dangerous than a simple error. When this flaw became obvious, the tech industry offered a seemingly simple fix. If the model does not know the facts, we will just give it a search engine. This pattern is called Retrieval-Augmented Generation, or RAG. The premise is straightforward. Before the model drafts an answer, a retriever search engine pulls relevant documents from a private database and pastes them directly into the model's temporary memory. But this is where everyone went wrong. Early adopters assumed that as model memory expanded to handle hundreds of thousands of words, we could just dump entire libraries into the prompt and let the AI sort it out. That assumption was a multi-billion-dollar mistake. Researchers quickly discovered the lost-in-the-middle phenomenon. When you feed a model a massive mountain of text, it pays attention to the very beginning and the very end, completely ignoring the crucial facts buried in the middle. Simply stuffing more data into the machine did not make it smarter. It just made its hallucinations harder to spot. To see how modern systems actually solve this, we must look at how AI translates human language into spatial geometry. Imagine a warehouse the size of a city. The items in this warehouse are not organized alphabetically or by category. Instead, every sentence, document, and concept is suspended in midair at precise spatial coordinates. This is the vector database. When a new document is added, an algorithm converts its meaning into a long list of numbers called an embedding vector. If two sentences share a similar meaning, they are placed close together in this multidimensional space. For example, a paragraph about a failing water pump and a paragraph about a leaking hydraulic valve will hang in the exact same aisle, even if they do not share a single word in common. When you ask a question, the system converts your query into a coordinate, fires a digital radar pulse, and pulls the nearest documents. This is cosine similarity. It is not searching for keywords. It is searching for conceptual proximity. But even this elegant spatial map has a breaking point. It works perfectly for simple questions, like what is the oil capacity of a specific engine? But it fails spectacularly when confronted with multi-hop queries. These are questions that require connecting multiple isolated facts across completely different documents. Imagine asking, did the director of the movie that won the King Grand Prize in 1994 ever study at Oxford? A standard vector database cannot answer this in one go. It first has to find the movie, then find the director, then find where that director went to school. Because the vector database can only search one neighborhood at a time, it gets stuck. It pulls documents about Cannes or documents about Oxford, but it fails to bridge the gap between them. It retrieves fragments of the truth, and when the generator tries to stitch those fragments together, the system breaks down, creating a brand new class of errors called retrieval distortion. To survive this bottleneck, the architecture of retrieval had to evolve from a passive database lookup into an active, multi-agent operating system. Instead of relying on a single search, cutting-edge architectures now deploy a network of specialized digital agents. When a complex query arrives, a planner agent breaks the question down into a sequence of logical steps. A retrieval agent fetches the first clue. A critique agent evaluates if that clue is actually relevant or just noise. If the information is incomplete, A refiner agent rewrites the search query and searches again, traversing a web of connected data points known as a knowledge graph. This is not just searching, it is active reasoning. By combining vector databases with structured graphs, these systems can trace the exact lineage of an idea, verifying every single connection before the language model is ever allowed to write a single word. But this advanced architecture comes with a steep price. In the rush to eliminate hallucinations, engineers have traded one set of problems for another. First, there is the tax of latency. A simple model call takes less than a second. A multi-agent, multi-hop retrieval loop can take 10 to 15 seconds of processing time, rendering it useless for real-time customer service. Then, there is the compounding cost. Running multiple search iterations, vector evaluations, and self-correction loops consumes massive amounts of computing power, multiplying the API costs of every single query. And finally, there is the risk of bias. If your retrieval algorithms are tuned too tightly, the system will only return safe, generic, or highly repetitive information. We have successfully stopped the AI from hallucinating creative lies, but we have also built a machine that is slow, expensive, and sometimes too timid to be useful. We are no longer trying to build a single, all-knowing artificial brain. Instead, we are building a digital bureaucracy, a complex web of checks, balances, indexes, and agents designed to keep a statistical prediction engine on the path of truth. Retrieval-Augmented Generation is not a magic wand that cured hallucinations overnight. It is a continuous, hard-fought engineering battle. In our quest to make machines think, we have realized that memory is not just about storing facts. It is about knowing how to find them, how to doubt them, and when to keep searching.